Today we're going to start chapter 4, which is reactions in an aqueous. Remember, aqueous means dissolved in water solution. And I'm going to show you some things like how to determine solubility and that kind of stuff. And hopefully I'm going to do this. I have this new scanner thing. I'm going to give that a shot. But first we got to talk about what these are. Okay. When you have a solution, it's a homogeneous mixture of two or more substances. Okay. So here, we have methanol and we have water mixed together. Okay. Homogeneous, again, remembering, or homogeneous if you like it that way, meaning it's mixed together well. You can't see the different parts to them. The methanol and the water in this case dissolve without, they mix together well. Okay. Whatever is in the greatest abundance is called the solvent, and most times your solvent is water. All right. Salt and water, sugar and water, things like that. But when we make a solution, there's parts to it. Okay. The other substance, so you have two substances. One dissolves, and that's called the solute, and one does the dissolving, and that's called the solvent. Okay. And like I said, water is the most common solvent. And when you say something is aqueous, that means it's dissolved in water. Okay. So when water is the solvent, it's called an aqueous solution. And again, aqueous means dissolved in water. And it's the most common thing. And water is called a universal solvent because it dissolves most things. So it does a good job. Okay, so an aqueous solution, water does a couple different things. The biggest thing with water, and the reason why it's so good at its job, is because it's polar. Remember, if you look here, this oxygen end is negative and this end is positive. So you have poles, and they can go in and here's a salt crystal with your sodium and your chlorine. They can actually go in there with their positives and negatives and separate them, okay? Because chlorine is negatively charged, so you can see here the oxygen's positively charged. The hydrogen part of the water the oxygen's negatively charged. Sorry about that. The negatively charged, see how all these oxygen are facing the sodium. Okay, sodium's positive. It's a cation. It's a +1. So now you can see they surround it and they separate it out. Okay, so an ionic compound, remember, an ionic compound is made out of a metal and a nonmetal. It has ions, positively and negatively charged particles. Because of those positively and negatively charged particles, water can help disassociate it. What happens is the water surrounds them and it's kind of like Pac-Man, just pulls them right out. Okay, if it's a molecular compound, some of them interact with water and some of them don't, like sugar will. Okay, but a lot of them won't dissolve because they don't have any poles, they don't have any positive and negative ends. The water doesn't break them down. Okay, some do, like sugar will. Okay, so some of them do, some of them don't. But one thing about them is the ionic compounds are going to be able to have charged particles in them, whereas not the moleculars won't. They will not have charges. Okay, so all substance dissolved by what they call solvation. Okay, and again, here you can see it. The water surrounds it and basically kind of, breaks it off. Okay, and again, all the positive hydrogen part of the water is going to be surrounded by the negative part. This would be the chlorine, the anion. And the negative part of the water, the oxygen end, is going to be surrounded the sodium, which is the cation, the positive. Okay. To give you an idea of what happens when they dissolve, if you have an ionic compound, if it's a strong electrolyte, what it means is when it dissolves in water, when you add water to it, it will conduct electricity. Okay. This is really important if you think about the battery in your car. We have battery acid. Battery acid is really sulfuric acid. But we add water to it and we seal it up. And then what it does is it conducts electricity. So when you pass a charge through it, it actually works. Okay, if you had other substances in there that weren't electrolytes, then your car's not going to start. Okay, so there's strong electrolytes, and that means they break down completely. And there's weak electrolytes. Okay, they're not fully committed. Okay, and then there's non-electrolytes. They don't conduct at all. Okay, so an electrolyte is a substance that dissociates in ions when dissolved in water. You might hear electrolytes like when the drinks, the sports drinks, Powerade, Gatorade, all that, they have electrolytes in it. That means they have sodium and potassium and chlorine, things like that. Because when you're dehydrated, you need more than just water. you didn't drink water and that's got you to that point. But when you sweat, you lose a lot of other ions. So these sports drinks replace those. And one thing you'll notice about them, if you drink one and you're not, really thirsty, or you're not haven't been particularly working out or sweating or whatever, they taste okay. But when you're really, really thirsty, when you've been really working out hard, you've been sweating, they taste amazing. Okay. Okay. So a non-electrolyte, it can dissolve in water, but when it does, it doesn't dissociate into ions. So like if you put sugar in water, yes, it'll dissolve. But if you try to pass a current through it, it won't conduct it. So sugar would be a non-electrolyte. Okay. Here's an example. If you take pure water, like distilled water, there's no ions in there. But if you take tap water, there's ions in there. Then it'll pass. Here's a non-electrolyte solution. Here's sugar. You pour sugar in, you pour water, nothing's happening. It's not going to conduct electricity. We're trying to pass electricity through there, but nothing's happening. But if you take salt, which is going to dissolve into cations and anions, positive and negatives, then it will, you can see, light bulb, bright as ever, because it conducts electricity. So this electricity is flowing through, gets to flow through all the way through to the light bulb and make it light up. Okay, so if it's a strong electrolyte, it completely disassociates. Salt would be that. It completely dissolves in water. Okay, a weak, partially. Okay, so if you had a weak electrolyte here, this bulb wouldn't nearly be as bright. It'll still conduct electricity, but not nearly as well. Okay, and then again, the non-electrolyte, like this. Sugar will dissolve, but it doesn't form any charged particles, so it doesn't. You can't, it doesn't conduct electricity. You don't want that in your car battery, okay? All right, so when you're looking at your strong and weak electrolytes, if a strong electrolyte disassociates completely, in other words, it completely breaks down into its little ions when dissolved in water, this would be an example. If you take the HCl is hydrochloric acid, okay, it becomes hydrogen ions and chlorine ions. Okay, a weak electrolyte, a lot of times you'll see the difference here. I only have the arrow. It means it just goes this way. It disassociates to these guys. But if you have it like this, that means this is acetic acid. Okay, what it means is it'll dissolve, but these guys will join back up again to go back here. So it goes both ways. So its equilibrium reaction, if you want to call that, goes forward and backward. So this forms these guys, but then these guys join up together and go back this way again. So you can tell the difference if you're talking about if it's a strong electrolyte. If you got the arrow pointing one way, that's a strong. If you got it going both ways, that's going to be a weak, because it'll form, these guys all join together again, the ions, and form this again. Okay. Okay, there's a solubility and there's rules, and there's a sheet that I have for you. So we're going to go through that separate. Okay, and what it does is, like if you have a double replacement reaction, you put two compounds together and you want to know if you're going to, does that reaction really happen? Well, you have to have a precipitate. Okay, you have to have something that's insoluble. If you have two things and you mix them together and then on the other side, both things are soluble, there's no reaction. You have to form a precipitate. One of them has to be insoluble. And I'm going to show you how to read those charts. The chart itself will be in this page, which you need to download it, but I'll show you how to use that. And again, it's a way of determining if a chemical reaction actually occurs, and it's excellent for double replacement reactions. Okay. Okay, so here's a precipitated reaction. Okay, so we have two compounds here. We have potassium iodide, and AQ meaning dissolved in water, and we have lead nitrate. Okay, so these two guys will separate when you put them in water. Okay, when you put them together, okay, then they form this nice precipitate. It's actually paint, you guys. Okay, so precipitates form. So yes, I know this reaction occurs. I end up with potassium nitrate and lead iodide. Okay, so I can look at my chart to figure out what that is. If I look at my solubility chart, it says nitrates are soluble. So it's not this guy. It says iodides are soluble except for, and then it has like silver, mercury, whatever, and one of them is lead. So this yellow stuff is lead iodide. It forms a precipitate. So you can use this chart, like I said, it gives you the rules for solubility. You can use the chart to figure out if a double replacement reaction will actually happen. Okay, so how do you predict whether a precipitate forms? Okay, so we got magnesium nitrate and sodium iodide. So sodium's going to go with nitrate and magnesium's going to go with hydroxide. Okay, so we look at the combinations, which we already got there, and then we determine whether they're soluble or not. Okay, and this one we can kind of tell because look, we got an S there. So we know this is a precipitate. It's kind of cheating, but you won't know that when you do these. But you look on the chart and it'll say nitrates are soluble. Okay, and it'll say hydroxides, some might be soluble, some might not, but magnesium hydroxide is insoluble. So here is a precipitate, so we know this chemical reaction occurs. And I think, yeah, that's where we're going to quit, because I want to show this to you so we can do some practice with the solubility, and then we'll move on to the next thing where we actually write out all the reactions for it. So we're going to quit right here, and then again I'll show you how to do these.